Hey everyone, it has been a long time since I've done one of these. Various other hobbies and real life has got in the way. I did say they would be at very variable intervals, although that hopefully is going to change soon, which I will get to later. So what are we talking about today? We are talking about a game project of mine called Killchain. And we're going to talk a bit about the game itself. We're going to talk about a series of videos I want to make about it, which hopefully people will enjoy. We're going to talk about what I call my marble collection, which is a bit of a technical look at some of the work for the game, and then we're going to look at what's coming next. So let's start with the game itself. The game is called Killchain. It is going to be a real-time strategy game, so somewhat inspired by old school RTS games, not name names, but you know, the classics. The idea, however, is that this will be implemented at global scale, so using modern processing to be able to run real-time strategy at global scale. And the main focus is on the chain of events from an observation to a battlefield effect. And this is going to involve some complex modelling of logistics, training, systems for R&D, and some AI. Not in the sense of language models, obviously, but it's kind of important to distinguish that these days. Then in the sense of combat AI that can learn and develop systems and strategies on its own. So yeah, that is the game. Trying to decide how much I want to share about that at the minute. I don't want to go too far into detail yet. Lots of it is likely to change. But the core idea is, like I say, from an observation to an effect. How does that happen? Including all the things along the way, the training of the people manipulating the equipment that causes that effect, the way that equipment is supplied to them, the way it's designed and developed, and the way those people are organised, coordinated, etc. So that's the game. So are these video series. So this is going to be a series of devlogs about the development of the game. So I am actually aiming for weekly releases. We'll have to see how that goes. I have been terrible at consistency and will probably remain so, but we'll see. It's an ambition. We'll get to why in a second. So I'm going to maintain the current production values, by which I mean no production values. This will be me recording some PowerPoints showing you some interesting parts of the game. And I would very much appreciate any comments and suggestions on direction, approach, results, that kind of thing. So why am I moving to a weekly series of videos, and what am I hoping to achieve with this? Well, firstly, it gives me some motivation. I'm seeing this as sort of like a sprint demo where I have to have something ready to show by the end of the week, which hopefully will help me do at least a little every week, and kind of slow, steady progress is more likely to get this done than inspired motivation, as it were. And then, secondly, some feedback. Like I say, intended as like a sprint demo, so people see things that can be improved, that could work better, that they think wouldn't be useful in the game, that they think would be useful in the game. Let me know in the comments, and I will do what I can. Can't guarantee I'll implement everyone's ideas. In fact, I almost certainly won't implement everyone's ideas, but it's good to have the feedback, and I will do the bits that I think are sensible. So what are the requirements for this game? And specifically, the thing I'm going to be talking about this video is the game needs a planet. I said it was a global scale game. That means you need a planet to fight over. And this planet needs to be procedurally generated, and it needs to be true scale. So one of the most interesting things about this game is the ability to run the same technologies, the same course of development, or at least the same systems underlying them, over multiple different planets, and see if you get the same outcomes, different outcomes, which bits line up, which bits don't. I think there will be some really interesting results there. Now, Running a complete campaign over historical time is going to take quite an investment of time, so it's possible no one will ever do this on multiple planets. However, I'm pretty sure I will, and I'm mostly building this game for myself, so yeah, that. Also, the AI is designed to be learning and adaptive to the point that you could just let it run and just let AI factions fight each other and still get interesting emergent results. So even if you don't have time to play a campaign all the way through multiple times, you could leave one running and compare it to one you have played, or compare it to another one that you've left running in the past, that kind of thing. True scale, because lots of the things I'm interested in only make sense with a big enough planet, so this needs to be a planet, or specifically Earth scaled planet. Complex terrain to fight over, obviously. Differences in ability to move through the terrain, differences in resource generation, tactical value, that kind of thing. So we need some way to procedurally generate a planet with that kind of terrain. It needs climate systems. The weather has been hugely important. Shouldn't conflate those two things, but weather and climate have both been hugely important to the outcome of conflict throughout human history, so we need that. It needs independent continents for various reasons, and it needs island arcs also for various reasons that I'm not going to get into. So the question then is, how do we procedurally generate a planet that meets all of these requirements? And this is where we get to my marble collection. So my marble collection is a collection of procedurally generated planets that I have built over the past 10 years, probably, so that's depressing. 5 years as a serious project. Yeah, I'm going to show you some of them, including the one that I'm currently working on for Killchain. So I'm going to show you a couple of historical ones first. So the first one is what I call the shiny planet. This was planet Earth. So we're using satellite imagery of the real Earth to texture a planet rendering system effectively. So it's mainly a testbed for atmospheric and land and ocean rendering techniques, atmosphere more than anything. And my newer planets don't look as good as this because I know how to do this now, so I haven't really been replicating it on every procedural planet I've worked on. I will get the procedural generation working and then replicate this, so I know I can achieve this look. So what does that look like? Well, this is close-up shot. I'm quite pleased with how this looks, although cloud rendering needs a lot of work, not enough self-shadowing. The self-shadowing isn't detailed properly, but that is something I'm not fully sure how to do, but I'm confident I'll be able to solve. From more of a distance, this is my procedural Earth, and this was 3D simulation. You can pan, zoom, fly around, which is quite cool. So that, when I can build a procedural planet that looks roughly like these two photos, that is a good sign that I've achieved my objectives. So, old procedural. So after this, I then tried to procedurally generate the landforms and continents, and not really been happy with any of these. And the big difficulty here is sort of understanding what correct looks like here, and there's lots of gut feel with this. So the biggest problem here is we only have one reference planet, i.e. the Earth, and knowing whether another planet would evolve exactly the way the Earth did or not, it is very, very difficult. So one example here that springs to mind and that I've been thinking about quite a lot lately is the Atlantic Ocean. So I'll get into plate tectonics a bit more in a future video, but as a basic primer, it's currently understood, or believed, based on the best evidence we have, that subduction of oceanic crust is the prime driver of plate tectonics. Now the problem here is that the Atlantic Ocean, the plates on either side of it, do not have any active subduction. Some of them border plates that are subducting, but none of the plates that make up, that border the mid-Atlantic ridge are actually subducting, so why is it moving? And there was a paper, 2023 I believe, that found a deep mantle upwelling below the mid-Atlantic ridge, which seems to be pushing it apart. And the question then would be, well, how common is that? firstly, what causes it if we want to simulate it, and secondly, how common is it? So we don't know what causes it. Currently an active piece of research, and if we want to simulate it, okay, we can't simulate the driver of it, but we could just put them in at random at some probability, right? However, what's the other probability? Because we know it has happened once, we haven't seen it happen anywhere else, but we only have one planet at this moment in time to look at. So it could happen every single time a supercontinent breaks apart, or it could be a one-off. We don't know. So how do you know if your simulation is producing the correct number of them? Well, you don't. So there's certain things. So there's a few approaches to this. First one is thinking about what the common continents of the Earth have, and there you're looking at things like mountain ranges, near subduction zones. You're talking about fore-arc and back-arc basins, things like that. You can look at how continents fit together, so continents that obviously were joined and have split, that's a big thing that makes it look right to me. Things like Orcologon basins, I can never pronounce that, probably getting it horribly wrong, which are things like the Amazon River Basin. And there are lots of other little sort of geological features that to me look right, combined with the requirements I was talking about earlier. So we need to build a procedural system that can generate all of that. And I finally think I understand enough about how the geology works to simulate it well enough to produce the features that I need. So this is one of my previous experiments, and you can see we have some of these features here. So we have plates that have clearly rifted off from each other. You can't really see these ones down here that well, but they do match, and you've got a bit of an island arc here where a bit of a plate has been pulled away. And I was very happy with this at the time, but it does have some problems. And we have another example here where you see clearly how the plates fitted together, particularly here, and this plate is rifted up here. But you can also see some of the problems here. So it tended to generate these very large sort of orange peely, long thin continents wrapped around the planet. It also was very hard to get those failed rifts that I was talking about producing basins, and when I moved on to the next stage of generating heights for ridges and mountain ranges, things like that, I found it very difficult to use the data generated by this stage of the simulation to move on to the next stage. So I have gone completely back to basics to start again, somewhat based on the old ideas, but a new simulation. So I started this about a week ago, and the plan is to combine real plate tectonic physics but with some very significant simplifications. And the current state of play is I have a ball with some cratons, a supercontinent, and some very non-realistic ocean plates. And then the plan is to use physics simulation to evolve this over about 2 billion years and hopefully produce a realistic outcome. So let's look through some of what we have done so far. So first step was to think about some practicality. You should always do this if you're starting a new project. So is this possible? Is it plausible? So some rough mental arithmetic. So generated a sphere, got to about 250,000 triangles, looks about detailed enough for my requirements. You're talking a medium-sized volcanic hotspot island will cover a couple of triangles, so that seems about right. This works out about 40 kilometers per edge, and maximum plate velocity we are aware of in history was about 20 centimeters a year. So assuming you only want to move half an edge in any given time step for the sake of stability of the simulation, making sure you don't have any interpenetrations and things like that. That runs to around 100,000 annum per time step, and given we want to cover 2 billion years, that means about 20,000 time steps, which if you manage to make it run at 10 FPS, that's about 40 minutes real time. So 10 FPS is for the procedural generation, it is not for the gameplay. I should point that out. This is not going to be running whilst you are playing the game. we don't need continents to move. You know, the whole of human history doesn't span enough time for that to be important. So yeah, 40 minutes. Now that to me seems reasonable. Obviously I'm not going to ask the players to sit and wait for 40 minutes before they start the game. What's going to happen is the game will ship with a number, where that number is somewhere between 10 and 100, depending on how much simulation time I can cram in, of pre-generated planets, but then they will be able to go and generate their own if they want, and if they want to sit there for 40 minutes to an hour, depending on how fast their PC is. And yes, this is going to be a PC game. So that seems reasonable. I'm happy with those numbers, so I think this has a decent shot at working. So the first thing we need then is a ball mesh, and this is surprisingly non-trivial to produce a ball mesh. So I'm using a subdivided icosahedron, and I just skipped ahead there, sorry about that. So if you don't know what an icosahedron, so there's a lot of different ways to make a triangle mesh of a sphere, and none of them are perfect. So if you want to know what an icosahedron is, it's this shape here. And what we do is we start with this shape and we subdivide it recursively until we have the number of polygons we want. So the subdivision looks like this. Basically what we do is we divide each triangle into 4 smaller triangles. And we do that by splitting each edge in half and then connecting those new points up. And we do that for each face, and we have a new mesh which has many more triangles, and it's still an icosahedron. And then obviously, because this is now made of more triangles, we can just subdivide each triangle further as far as we want, and this will produce as big a mesh as we would like, or as detailed a mesh as we would like. Now obviously, because you're subdividing existing triangles, you can't say I want exactly this number, so what we do is we say I would like more than X number of triangles. So I am asking for 100,000 and I actually end up with 250,000. 250,000 so far is running fine performance wise, so I'm happy with that, and it's about the right level of detail, so yes, that's what I'm going with. And then once you've got all your triangles, you just push them all out onto the surface of a sphere, and then that produces something that looks like this. Now this also produces some degenerate vertices, so we need to uniqueify them, which means just walk through the mesh and for each vertex check if it's in the same position as any other vertex. A little trick to make this faster, there's lots of ways of doing that, using grids, trees, whatever. What I'm doing is just subsampling every 100th vertex and then creating lists of the nearest vertices to each of those. That would be 1,000 vertices, so you get 1,000 lists of vertices, and then you only ever need to check each vertex against the other vertices in that list. And that took the naive n-squared algorithm was about 2-3 minutes, and now it's about 2 seconds, which is entirely fast enough as a one-time process. And then finally we also walk through and build a list of neighbours. Now you know the faces to build the mesh, obviously, so finding the neighbour list is fairly easy. It isn't the same as the face list though, and that's an important distinction. So that's our mesh. Now you might notice there are some triangles, large triangles visible. These are the original faces of the icosahedron. These are visible because the kind of orientation of the triangles changes slightly, like the bigger lines are at slightly different alignments. That almost certainly won't show up. If it does, we can just add a tiny bit of jitter to this mesh and it will go away completely. We'll see what happens when we get into rendering something interesting. Right, so step 3 is to make this a slightly crunchy ball. What do I mean by that? So there's lots of processes where you need to pick a region and grow it for some reason, at least in your initialization. And I found if you do that just by growing by surrounding points, if you've got some randomization in, it tends to get quite circular patches quite quickly, or at least very smooth patches, and I want something a bit crunchy. I also want to be able to run some of these processes quite fast, so I only want to be considering regions of points rather than individual points. So what I've done here is just build a very simple Voronoi subdivision of the overall mesh, which you can see here on the right. If you don't know what a Voronoi subdivision is, so it's a very simple process. Basically, select a random number of points in select a number of random points in the space. These don't have to be points on the mesh. Mine are, because rather than generating new points, I'm just selecting existing points pretty much at random. And then for each point you assign for each large point you assign all of the... No, that's a horrible way to explain it. Walking backwards. For each point on the mesh, you assign that point to a group based on which large control point it is nearest. So each control point has a group of vertices assigned to it. Those vertices are the vertices which are nearest to that control point. What that ends up doing is dividing space like so. You end up with lines between each pair of points, and then any subpoint within this region will all be assigned to this point, within this region to this point, this region to this point, etc. And that produces the results you've seen before. Very fast, produces good regions, works, does what we need, very simple, I like it. Next thing, cratons. Right, okay. So, you may or may not know anything about tectonics. I'm not going to get into it in detail, but the Earth's crust essentially comes in two flavours, oceanic crust and continental crust. So, as the name implies, oceanic crust tends to be where you find the oceans, or rather beneath the oceans. And continental crust tends to be where you find the continents, or specifically the land. So, within this, or rather within continental crust, you have things called cratons. I'm being a bit loose with the terminology here, but essentially cratons are very stable areas of continental crust. Now, we don't actually understand how these formed, so I'm just going to make some. And these are very, very important for defining the bulk shape of the Earth's continents, and they haven't changed in billions of years. They formed somewhere between 1 and 3 billion years ago, and they haven't really changed very much since. So, like I say, we don't entirely understand the processes that form them, so instead what I'm going to do is define how much of the planet's surface we want to contain a supercontinent. We'll get to supercontinents later. And then we'll pick a number of points in that area, and then mark any of the cells we just talked about that are within a certain distance of each point as cratonic, and this should create several cratonic regions. So what we get when we do this looks like this. So there is a problem here, which is that this image should show 20 or so individual cratons. What it actually shows is 3 cratons, and this is because actually we've generated 20 or so, but they're all neighbouring each other. Now, given the way the simulation is going to work and what I just said about cratons being very stable, and specifically cratons will never split apart, that means we will only ever have 3 cratons and not much will happen. So how do I solve this? Well, it's actually very simple. Basically we track the border of each craton and mark it as ordinary crust, and this is falling back on that thing I said about knowing the neighbours of each point. So basically for each point in a craton, if the neighbours of if any of that point's neighbours are not in the same craton, we just mark those as continental rather than cratonic. If we do that, we get this result. Now obviously this is a different random generation, but you can see the same thing. We would have had 2 here, we now have 20 or so. So this has worked pretty well, and I'm happy with this. I would note at this point I'm not actually showing any code today. I may show code later, I may not. I said right at the start of these videos, this isn't a coding tutorial, it's more an explanation of processes and results. Like I say, more like a sprint demo plus some theory. Nothing here is particularly challenging to code once you know what you're trying to code. So anyway, we have cratons. Woo! Next thing is we need a supercontinent. So several times throughout Earth's history, all of the land has been fused together into one massive continent, which included the cratonic and non-cratonic crust. Continental crust, that is. Now, this we are going to use as the starting point of our simulation. So we're starting about halfway through Earth's history, slightly over. And we're hopefully going to form multiple of these supercontinents over time through the simulation, but we're going to start by just building one. And the non-cratonic crust within these supercontinents, that's where most of the interesting stuff happens. It's where the supercontinents split apart, it's where they mash back together, it's where mountains form. So, to build this, we are simply going to take the same region we defined for the cratonic regions. That is the big region that the cratons are allowed to form in, not the little cratonic subregions. And we're going to select some of those oceanic Voronoi regions and mark them as continental. And we'll just keep going until we have as much continental crust as we would like. This will just be a parameter simulation. Currently I'm using basically the parameters of the current Earth. This could loop infinitely, obviously, if we didn't have enough crust available. Never going to happen in reality. The region is always more than big enough. If ever it did happen, you just put a simple counter in and give up at a certain point in the loop. Not something we need to bother with. One slight problem here is this tends to produce a very circular supercontinent, so we could fix this by using various subregions, and then sometimes you get circular ones, sometimes you get lines, sometimes you get L-shapes, but I don't think that's really necessary because physics simulation is going to completely reorganise this. It's going to rip it apart and push it back together at least twice. So I really don't think we need to bother with that yet. If that isn't the case, if I'm not happy with the results, I'll just go back and go to a slightly more complicated multi-region supercontinent. We'll see. So then this is what a supercontinent looks like. So obviously yellow is continental crust and grey is cratonic crust, and then the blue is oceanic. And you can see sort of if this gets pulled in half, you'll get some interesting shapes, and the cratons will form like stable masses within the continents, and then they'll have interesting borders around them. And that's kind of what we're going for. So next thing we've done. So we're nearly there, we're nearly caught up with where I have got to, so the next step is to create the ocean plates. So the Voronoi cells are far too small to represent ocean plates, we need them to be much bigger. So the approach is really simple here. If a cell is too small, then we know the neighbours of each point in the cell. Some of those neighbours will be in other cells. Those cells must be neighbouring cells, so just merge a neighbouring cell into the current cell. Repeat until all cells are now large enough. Produces good sized continents of varied shapes, nice and crunchy, which is sort of what I wanted. Very unphysical. There is no way real geological processes could produce continents this shape and distribution. That is entirely fine, and this was one of the problems I had with other approaches to procedural planet generation, was you would get these very glaringly non-physical continents. Obviously these aren't continents, these are ocean plates. You can see at the top there, the blue, that is the supercontinent that is land. All the other colours are different ocean plates. So this is not a problem here, because we are then going to run 2 billion years of geological tectonic simulation, which will completely reshape these. None of these plates will last more than about 200 million years. They don't on Earth. And 250 maybe. Need to check that. And the new ones that will form should be much more, well, they will be physically plausible because they will have been produced by a physical simulation, even if a very simplified one. So yes, run a physics simulation, let it sort things out. And yeah, this is just a starting point to get the whole process moving. Again, how the Earth's crust originally formed into plates and fractured and started moving is also not currently known. There are theories trying to build something that can simulate that. One, because we don't know how to do it, we don't know if it would be accurate, and two, trying to do it would be hard, so I'm not going to bother. We will get very, very similar results this way, and there's no way to say that doing it the other way would actually be more accurate, so we're going to do it the easy way. And then the final step was to make the plates move. So real plates aren't static, they move. I talked earlier about the Atlantic Ocean widening, so the Americas are moving away from Africa and Europe at a couple of centimetres a year, and we will want to simulate things like that. So for now we're just going to assign a random direction and speed. This is where a lot of current planet generators, even the most advanced ones, stop. For us this is just the starting point, but it proves that we can move plates around and then map them back onto the mesh, because fundamentally we need to push those points back to the mesh. And there's a little interesting trick to make this quick. So two things we said earlier is, one, we know the neighbours of every point, and two, no plate, and hence no point within a plate, is ever going to move more than half of a triangle. What this means is that after you have moved a point for a time step, you are guaranteed to be trying to map onto either that point or one of its neighbours. So instead of having to search through the whole mesh or a tree of the mesh or something similar, all you have to do is search through the direct neighbours of that point to find the current point that that vector is now mapping to. So let's have a little look at that. So we have a video here, and as you can see the plates are all moving around the globe. I'm rotating the globe a bit for you. So one interesting effect, you can see the plates trail. That's because we're not clearing them before they move. That's fine, not expecting any problems from that for various reasons. Something that is possibly slightly more worrying is here you can see this red plate and the white plate are overlapping. Again, the physics simulation will actually stop that happening, but you can see that not all of these red points have been filled in. The red is clearly being assigned after the white or beige, whatever it is, and so there are some holes here. Now I do not believe that will be a problem because of the way I'm intending the simulation to work, but there is a small chance it might. If it is, I have a solution to that in mind, so we'll see how that goes and where we get to. And that is where we are. We have a planet with some initial cratons, some initial ocean plates, initial continental crust, all continental crust and cratons all combined in one supercontinent, and we can move the plates around. So the question is, where are we going next? So the next step is to work on actual plate tectonics. So this is the forces that move plates around and make the continents look the way they look, make mountains, make large river basins, all that kind of thing. So next week I'm going to start trying to get the plates to move due to actual geological forces, and this is the start of the physics simulation. We're going to start with subduction. This is the main driver of plate movement in the world, and I'm hoping to get that, at least the physics of plates subducting and moving, to work. Hopefully I will also get as far as forming new crust where the plates have moved away and assigning it to plates, or possibly forming island arcs above the place that the plate's subducting. If I can get either or both of those done, I will be very happy. Depends how busy I am this week. As a very long shot, there is another phenomena called mantle drag, which is going to be important for the next stages, and if I can get that done as well, that will be super. Consider that a massive stretch goal. And then for the future, looking forwards, the next things to look at are rifting and supercontinent breakup, so how we start to break that supercontinent apart into multiple smaller continents. So yeah, that's where we are, that's where we're going. I will update you next week. Thanks for taking the time to listen as ever, and as I mentioned earlier, feedback, suggestions on this project, very much appreciated. Yeah, we'll take on board anything constructive. Thank you.